A heap is a special type of tree with two properties. The first property is that it's a complete tree, which means every level, except potentially the last level, is completely filled, and levels are filled from the left to the right. So here we have a complete tree because every level is completely filled with nodes. Here's another complete tree. Both the first and second levels are filled. The last level is not filled, but nodes are filled from the left. So we still have a complete tree. But this tree is not complete because here we have a hole in the last level. As I told you, in a complete tree, levels should be filled from the left to the right. Here's another example of a tree that is not complete. The second level is missing a node. So in a complete tree, every level except potentially the last level should be full of nodes, and nodes are inserted from the left to the right. Now, the second property of a heap is that the value of every node is greater than or equal to its children. This is called the heap property. So if you have 20 in the root, the children of this root should be less than or equal to 20. Both 10 and 15 are smaller than 20, so they satisfy the heap property. Similarly, the children of these two nodes are smaller than the nodes themselves. However, if we replace 15 with 21, now we don't have a valid heap because 21 is greater than 20. Let's revert this back. So a heap is a complete binary tree that satisfies the heap property. Now what we have here is called a max heap because the root node holds the largest value, and as we go down in the tree, values get smaller. We also have min heaps where the root node stores the smallest value. And this heap that we have here is more accurately called a binary heap because it's a binary tree. Now let's talk about the applications of heaps. Heaps have many applications. We can use them for sorting data. In fact, we have an algorithm called heap sort. We'll look at that in the future. Heaps are also used in implementing graph algorithms. For example, we can use heaps to find the shortest path between two nodes in a graph. This is the algorithm that powers your GPS. We'll look at that in the future. Heaps are also used in implementing priority queues. Again, we'll look at that later in this section. Another application of heaps is in finding the kth smallest or largest value. This is a very popular interview question, so we're going to explore it later in this section. Now let's talk about the operations of heaps and their runtime complexity. So we're going to populate our heap with these numbers. While populating this heap, we want to make sure that we satisfy the heap property. So the value of every node should be greater than or equal to its children. To do this, we insert a new item in a leaf node, and if it's not in the right position, we move it up until it's in the right place. We start by storing 10 in the root. Now we want to add 5. The first level is full, so we go to the second level and start filling the tree from the left. So we store 5 over here. Now we have a valid heap because the root is greater than its child. So let's insert 17 in the next empty slot. Here we are violating the heap property because children of the root should be smaller than or equal to 10. So we should move the 17 up. This is called bubbling up, just like the bubbles in your soda. They move up. So we should bubble up the 17. And now we have a valid heap. So let's store 4 in the next empty slot. Is our heap valid? Sure it is. So let's move on to the next number. We store 22 in the next available slot. This 22 is violating the heap property, so we have to move it up. We basically swap it with its parent. Now, is our heap valid? Not yet, so let's move it up one more time. Now the 22 is in the root and we have a valid heap. So in a max heap, large values bubble up or move to the top. If we had a min heap, small values would bubble up, okay? Now, what is the time complexity of this operation? Well, the longest a value can travel is equal to the height of the tree. This is similar to finding a value in a binary search tree. In a binary search tree, if you want to find a value, we start from the root and we travel down the height of the tree until we get to a leaf node, right? Now, bubbling up an item is the same in terms of the number of comparisons we need, but it happens in the opposite direction. What is the time complexity here? It's an O of log n. Also, in math, we can prove that in a balanced binary tree with n nodes, the height of the tree is equal to the logarithm of n. This is the reason why the time complexity of searching for a value in a binary search tree is O of log n, because the maximum number of comparisons we need is equal to the height of the tree. So we could either say O of log n or O of h. H equals log n, okay? Now let's look at deletion. In heaps, we can only delete the root node, not one of the inner nodes. So let's remove the 22. Now we have to fill this root node with another value to maintain the heap property. We want to make sure that our tree is a complete tree, so every level except potentially the last level should be filled from the left. To maintain this property, we can move the 5 to the root. Now, do we have a valid heap? Of course not, because 5 is smaller than both its children. To solve this problem, we should move the 5 down the tree. This is called bubbling down, which is the opposite of bubbling up. Now, to move the 5 down, we should look at its children. We pick the larger one and swap it with the 5. The larger is the 17, so we should swap it with the 5. And now we have a valid heap. If our heap was not valid, we would keep bubbling down the 5 until it's in the right position. Now, what is the time complexity of this operation? Again, the longest the root node can travel down is equal to the height of the tree, which is equal to the logarithm of n. So removing the largest value in a heap also runs in logarithmic time. Another operation we can perform on a heap is finding the maximum value. Here we have a max heap, so finding the maximum value is super easy. We simply return the value of the root node. This operation runs in constant time, or O of 1. Now, if we had a min heap, we could quickly find the minimum value by inspecting the root node. So this is how heaps work.